We're going to find the singular value decomposition for matrix A. We're going to start by finding A transpose A. So we know that we can break down A into a product of U, sigma, and V transpose, where sigma is our singular values, V is the eigenvectors that we get from A transpose A. Okay, so A transpose A is going to be 1, 0, 1, negative 1, 1, 0, times A, 1, 0, 1, minus 1, 1, 0. So this gives us a 3 by 3 matrix. And we get 1 plus 1 is 2. We get 0 minus 1. We get 1 and 0, so that's 1. We get negative 1, get that by symmetry. 0, and then 1, and then 0, 0. And then 1 and 0 is 1, and then 0 and 0 is 0, then 1 and 0 is 1. Okay, so that gives our A transpose A matrix. Fantastic. Now, we need those eigenvalues. So we have 2 minus lambda, minus 1, 1, minus 1, 1 minus lambda, 0, 1, 0, 1 minus lambda. Okay. So when you work this out, and I'm not going to do it here, but when you work it out, it factors to be lambda, lambda minus 3, and lambda minus 1 equals 0. Right, so just follow the minors, use the Laplace method. It'll be okay, you'll figure it out. But you've got lambda equals 3, 1, and 0. So this gives you sort of a place to start. So our sigmas are going to be root 3, 1, and we're not going to have a 0, but we'll hang on to it anyway. Great. So our sigma matrix, the reason we knew that we weren't going to have the 0 is because our sigma matrix has to have the same dimension as A. So we go root 3 and 1 on the diagonal, and we fill in the rest of the zeros to make it the same dimension as A. Okay. So this gives us, we've got our we've got our sigma, now we need our U and our V transpose. To find our V, we have to find all of the eigenvectors. So let's start with lambda equals 3. When we try lambda equals 3, we end up with 2 minus 3 is minus 1, then minus 1, then positive 1, then minus 1. 1 minus 3 is minus 2, and then 0. 1, 0, and 1 minus 3 is minus 2 again. All right. So the relationships we get here is that x is equal to 2z, x is equal to negative 2y. And of course, that x plus y is equal to z. So if we allow z to be 1, that forces x to be 2, and it forces y to be negative 1. We need to normalize that. So this has length 2 squared is 4 plus 1 is 6. So 1 over root 6 to normalize. Okay, and that's our first eigenvector in V. Next, we'll go with lambda equals 1. So 2 minus 1 is 1, negative 1, 1, negative 1, 1 minus 1 is 0, 0, we've got 1, 0, and 1 minus 1 is again 0. So the main relationship, or the first relationship we see here, is that x has to be 0, and then y is equal to z, is the relationship captured in the first row. So we're going to have something where x is 0, and then y and z are the same, so 1 and 1. So we'll go 1 over root 2 times that vector for our second eigenvector in V. Our third eigenvector, our lambda equals 0, I'm trying to squish it in here, gives us a matrix 2, negative 1, 1, negative 1, 1, 0, 1, 0, 1. And so line 2, we know that x is equal to y. We know that x is equal to negative z from the third line. And the first line is 2x plus z is equal to y. So if we let x equal, well, let's let z equal to 1 again. That forces x to be the negative of that, so negative 1. And because x is equal to y, we get negative 1 there as well. And so 1, 1, 1 is 3, so 1 over root 3 times that vector. So this gives us our vector V. So 2 over root 6 in this vector here, negative 1 over root 6, and 1 over root 6. Vector 2 is 0, 1 over root 2, 1 over root 2. And then from vector 3, negative 1 over root 3, negative 1 over root 3, and 1 over root 3. Okay, that gets us our sigma and our U transpose. V transpose. Now all we have to do is find U. Now U is a 2 by 2 matrix because we've got a 3 by 3 matrix that's going to be multiplied on the left by a 2 by 3 matrix. So the result is going to be 2 by 3, which means that we need a 2 by 2 for U. So U1 is going to be 1 over sigma 1, so 1 over root 3, times matrix A, 1, 0, 1, minus 1, 1, 0, times our first vector V. So that's going to be 2 over root 6, negative 1 over root 6, 1 over root 6. Okay. The root 6 times the root 3 is going to give me 3 root 2 on the bottom. All right. So then I can multiply without worrying about that division here. So I've got 2 and 1 is 3. Then I've got negative 2, negative 3 here. And very convenient, the 3's are going to cancel. So 1 over root 2, 1, negative 1. Okay. U2 now is going to be 1 over 1 times A times my second vector, which was 1 over root 2, 0, 1, 1. So we'll bring the 1 over root 2 out front. And I've got my vector here. So 0, 0, 1. And then 0, 1, 0. So 1 over root 2 times 1, 1, which makes my matrix U 1 over root 2, negative 1 over root 2, 1 over root 2, 1 over root 2. And so A is equal to U sigma V transpose, where U is our matrix here, sigma is our matrix here, and V transpose is the transpose of this matrix here.